Dear students, welcome back. In previous class, we discussed the complete residue system. So now let us discuss the reduced residue system and the Euler-Fermat theorem. So what is a reduced residue system? Reduced residue system means a set of phi of m integers. Phi of m means it is Euler torsion. Phi of m is it is Euler torsion function, phi Euler torsion. So a set of phi of m integers in congruent mod m, each of which is relatively prime to m, is called a reduced residue system. A set of phi of m integers, a set of phi of m integers which are in congruent mod m, and each of which is relatively prime to m is said to be a reduced residue system, where phi of m is nothing but the Euler torsions. So, now come to a theorem. If a1, a2, etc., a phi of a phi m be a reduced residue system mod m, and if k and m are relatively primes, then the multiples ka1, ka2, etc., ka phi m be also a reduced residue system mod m. Since a1, a2, etc., a phi m forms a reduced residue system mod m, means we have ai is in congruence to ha mod m, or ha in congruence to ai mod m for all I differs from j. If possible, Kai is congruence to Kaj mod m, then it is given K and M are relatively primes. So by the cancellation law, immediately we can conclude that Ai congruence to Aj mod m. That's a contradiction. That is not possible because say A1, A2, etc., A phi m forms a reduced residue system. Therefore, we can conclude that Ki in congruence to Kh mod m. That means this Ka1, Ka2, etc., K phi m also forms a reduced residue system, complete residue system. Now we have, since K and M are relatively prime, K and M are relatively prime, therefore K, A, and M are also relatively primes. Therefore, it satisfies the definition of reduced residue system. Hence, no two of the members Ki are congruent to each other. No two of the members of Ki are congruent to mod m. Also, GCD of Ki and M is 1, means Ka and M are relatively primes. Hence, the multiples of the products Ka1, Ka2, etc., Ka phi m always forms a reduced residue system. Agree? Now, by using this fact, we define Euler-Fermat formula. What is Euler-Fermat theorem? The theorem says that if GCD of A and M, or if A and M are relatively primes, then A power phi of m, congruence to 1 mod m. A power phi m congruence to 1 mod m. So how? Its proof is in this way. If A and M are relatively primes, then A power phi m congruence to 1 mod m. So if B1, B2, etc., B phi m, that is phi m, set of phi m integers, forms a constitute a reduced residue system mod m, constitute a reduced residue system mod m. Let A fall in set. Let A is any integer with A and M are relatively prime. Okay. Then, since B1, B2, etc., B phi m forms a reduced residue system, A and M are relatively prime, then by the previous theorem, we know that the set of integers, etc., A B1, A B2, etc., A B phi m also forms a reduced residue system mod m. Okay. Yes. Thus the product of all integers in the first set. The product of all integers in the first set is congruent to the product of all integers in the second set. What is the first set? B1, B2, etc. B phi m forms a reduced residue system mod m. Then since A and M are relatively prime, the product, the multiples A, B1, A, B2, etc. A, B phi m also forms a reduced residue system mod m. Then the product of all integers in first set congruent to the product of all integers in the second set. That means A B1 into A B2 into etc. into A B phi m is congruent to this B1 into etc. Bm mod m. Okay, so that means this A power phi of m into B1 etc. Bm B phi m is congruent to B1 etc. B not Bm B phi m mod m B phi m mod m. Okay. So that means A power, what is Bi? Clearly, since each Bi and M are relatively primes. Why? Because B1, B2, etc. B phi m forms a reduced residue system mod m. That means each Bi and M are relatively primes. Since each Bi and M are relatively primes, the cancellation law hold here. That means A power phi of m is congruent to 1 mod m. This is nothing but the required theorem. So that is the Euler-Fermat theorem. If A and M are relatively prime, then A power phi m is congruent to 1 mod m. Here we can constitute a reduced residue system mod m. Since each Bi and M are relatively prime, then in this step the cancellation law is possible. Therefore A power phi m is congruent to 1 mod m. Okay. Now come to a corollary of this result. If P does not divide A, then A power P minus 1 is congruent to 1 mod P. If P does not divide A, then A power P minus 1 congruent to 1 mod P. P does not divide A means we have A and P are relatively prime. P does not divide A means A and P are relatively prime. Since A and P are relatively prime, Euler-Fermat theorem states that A power phi of P congruent to 1 mod P. Okay. Since P is not prime, since P is prime, what is phi of P? Phi of P is P minus 1. Since phi is Euler torsion, so it is A power P minus 1 is congruent to 1 mod P. That's immediate. So this is a corollary of Euler-Fermat theorem. If P does not divide A, then A power P minus 1 congruent to 1 mod P. Okay. Now you consider another result, that is little Fermat theorem. This is Euler-Fermat theorem, and now we consider little Fermat theorem. What is little Fermat theorem? The theorem states that for any A following set, for any A is any integer A, comma, and any prime and any prime P, for any integer A and any prime P, then A power P congruent to A mod P. A power P congruent to A mod P. For any prime, for any integer A and any integer, and for any integer A and any prime P, then A power P is congruent to A mod P. This is little Fermat theorem. Euler-Fermat states that when A and M are relatively prime, then A power phi m is congruent to 1 mod m. But little Fermat theorem states that A power P congruent to A mod P for any integer A and any prime P. How? If P does not divide C, first case, it's proof. If P does not divide C, P does not divide C means A and P are relatively primes. Then since A and P are relatively primes, and what is phi of P? Therefore, since P is a prime, phi of P equals P minus 1. Phi of P is P minus 1. Then by Euler-Fermat theorem, A power phi of P congruent to 1 mod P. That means A power P minus 1 congruent to 1 mod P, since phi of P is P minus 1. Okay. Now a power p minus 1 congruence to 1 mod p, since p does not divide a, but we have a congruence to a mod p. Sure? Yes. A congruence to a mod p. Therefore, a power p minus 1 is congruence to 1 mod p. So that means a into a power p minus 1 congruence to a mod p. That means a power p congruence to a mod p. So this is when p does not divide a, then a power p congruence to a mod p. If p divides a, what happens? If p divides a, p divides a means p divides a, that means a is a multiple of p. Okay, a is a multiple of p. A is a multiple of p means a congruence to 0 mod p. A is a multiple of p means a congruence to 0 mod p. A congruence to 0 mod p, mark it as 1. Again, its power, a power p is also congruence to, if a congruence to 0 mod p, immediately a power p congruence to 0 mod p. That means, that is marked as 2. So 1 minus 2 gives, 1 minus 2 gives, or 2 minus 1 gives a power p minus a congruence to 0 mod p. 2 minus p, 2 minus 1. That means a power p congruence to a mod p. So when p divides a, it is proved by using Euler-Fermat theorem, and when p does not divide a, it is the little Fermat theorem is proved by using Euler-Fermat theorem, and when p divides a, it is proved by this argument. When since p divides a congruence to 0 mod p, a power p also congruence to 0 mod p, then subtracting a power p minus a is congruence to 0 mod p, that means a power p congruence to a mod p. Agree? So now there is a theorem. If a and m are relatively primes, if a and m are relatively prime, the solution, there is a unique modium of the linear congruence. Consider the linear congruence ax congruence to b mod m. B mod m is given by, if the solution, the unique solution mod m is given of this linear congruence is given by x congruence to b into a power phi of m minus 1 mod m. So the theorem is important. If a and m are relatively prime, then the solution to the linear congruence ax congruence to b mod m is x congruence to b into a power phi of m minus 1 mod m. How? This proof is, come to the proof. By Euler-Fermat theorem, we know that by Euler-Fermat theorem, we know that we have a power phi of m congruence to 1 mod m if a and m are relatively primes. A and m are relatively prime is a given condition. GCD of a and m is 1. Then by Euler-Fermat theorem, a power phi m congruence to 1 mod m. Okay. So that means b into a power phi of m is congruence to b mod m. Okay. So that implies b into a power phi of m congruence to b mod m means by we can rewrite as b congruence to b into a power phi of m mod m. Why? Because of symmetry of the congruence. Congruence relation is always symmetric. Congruence relation is symmetric. Why? That is if there is a congruence to b mod m should implies b congruence to a mod m. So b a power phi m congruence to b mod m implies b congruence to b a power phi of m mod m. Agree? That is ax congruence to b mod m is given. Consider the linear congruence ax congruence to b mod m. And also we know that b congruence to b a power phi of m mod m. The congruence relation is always transitive. So from here you can conclude that ax congruence to b a power phi of m mod m. Why? Because congruence relation is transitive. Congruence relation is transitive. So from here, that means x congruence to b a power phi of m minus 1 mod m. B x congruence to b a power phi of m minus 1 mod m is a solution of ax congruence to b mod m. Therefore, since x and what is a and m, since a and m are relatively primes, then according to the previous result, a and m are relatively prime, then ax congruence to the linear congruence ax congruence to b mod m has a unique solution. That solution is x congruence to b a power phi of m minus 1 mod m. Agreed? So this is the regular result. Enough. Okay. Now, by using these arguments, by using this theorem, we can try to solve a problem. So, find the solution of the linear congruence 5x congruence to 3 mod 24. 5x congruence to 3 mod 24. Solve this linear congruence. 5x congruence to 3 mod 24. So here we can compare it with the linear congruence ax congruence to b mod m. Okay. So what do you get? Here a equals 5, b equals 3, m equals 24. What is GCD of a and m? A and m means GCD of 5 and 24. That is 1 means a and m are relatively prime. When a and m are relatively prime, then ax congruence to b mod m has a unique solution. So since 5 and 24 they are relatively prime, hence 5x congruence to 3 mod 24 is also has a unique solution. Agreed. What is the unique solution? The solution is, according to the previous argument, it is x congruence to b into a power phi of m minus 1 mod m. Okay. That is x congruence. That is x congruence to what is b? 3. A, what is a? 5. Phi of m, phi of 24 minus 1. Phi of 24 minus 1 mod m means 24. Enough. What is phi of 24? Phi of 24 means phi of 3 into h. Okay, 3 into 2 cube. That equals phi of 3. What is, so it is phi of 3 into phi of h. Since 3 and 8 are relatively prime, if m and n are relatively prime, phi of mn, using the Euler-Torsion relation, phi of mn equals phi of m into phi of n, since if m and n are relatively prime. So here 3 and 8 are relatively prime, so phi 3 into 8 equals phi of 3 into phi of h. What is phi of 3? 2. Okay, what is phi of h? Come on, what is phi of h? Phi of 8 is, yes, try to find out this phi of 8. Phi of 8 is 4. That is 8 itself. Phi of h, then integers primes to h and less than 8 equals h. So it is 1 and 8 are relatively prime, 3 and 8 are relatively prime, 5 and 8 are relatively prime, 7 and 8 are relatively prime, so phi of 8 is 4. So phi of m is 2 and phi of 8 is 4, so phi of 3 into 8 is 8 itself. So now x congruence to 3 into, therefore x congruence to 3 into 5 power phi of 24 means phi of h, so it is 5 power 8 minus 1 means 5 power 7. So it is 5 power 7 mod 24. Okay. What is 5 power 7? 5 power 7 is again 5 with respect to in modulo 24. 5 power 7 is in modulo 24. 5 power 7 is 5. Why? We know that 5 square equals 5. Sorry, 1. In modulo 24, 5 square is 1. Why? In modulo 24, 5 square is 1. 5 square 25. 25 minus 1 24. So 5 square whole cube equals 1 cube or congruence to 1 cube mod 24. Okay, 5 square is congruence to 1 mod 24. So 5 square whole cube is congruence to 1 mod 24. Therefore 5 power 6, 5 power whole cube means 5 power 6 congruence to 1 mod 24. That means 5 power 7 congruence to 5 mod 24. Okay, so 5 power 7 congruence to 5 mod 24. Therefore this x congruence to 3 into 5 power 7 means 5 mod 24. So that means x congruence to 15 mod 24. So this is the unique solution. Since a and m are relatively prime, it has a unique solution. Hence it is x congruence to 15 mod 24. Okay. Now we consider another problem, that is solve the linear congruence 25x congruence to 15 mod 120. 15 mod 120. So tries to solve this. Here a equals 25, b equals 15 and m equals 120. Here a and m, GCD of a and m equals 25 and 120. This is differs from 1. It is not a 1, it is equals 5. So d equals 5. D equals 5. Hence there exists the linear congruence ax congruence to. Therefore the linear congruence ax congruence to b mod m has 5 solutions. For 4 solutions, then you can find out the solutions.